Okay, well, as it turns out, it looks like I'm wrong. So we have an expert here who's joining us, Ron Demcko from AVX. Thank you, Ron. You're going to tell us what I've got wrong, because I thought this was a self-healing issue, but you don't think so.
Yeah, I think we could give you some details on the real event.
All right, thank you. So what's your role at AVX? How long have you been there?
Well, I just passed 40 years. And
Whoa.
So I've been here for a while. Yeah. Well, it's funny, though, because the company changes. So every 3 or 4 years, we buy a new division. So at one point in time, it was just capacitors. Now it's antennas, connectors, modules, a whole bunch of other things. So, yeah.
Right.
I work in a small group in R&D, and we do engineering support, things like that.
Got it. But you're the capacitor guy, right? You're in the capacitor. Yes. Yep. That's your specialty. 40 years in 40 years in capacitors?
Well, yeah, different types: glass, tantalum, electrolytic, ceramics.
Tell us your opinion. What am I seeing here? What do you think this problem is? Because you don't think that it is being destroyed by impulses on the mains. That's
right. Yeah. Well, I think we should start going back and looking at the parts. So mainly these parts are non-hermetic. They're using a low-cost epoxy. So, they're very cost-effective, easy to use, easy to choose. So it's a probability that moisture got in the application. And then that moisture was trapped with that non-hermetic case. So what we have, well, there's also another scenario. There could be poor drying in the manufacturing process, and possibly materials were, water was put in there. That's very unlikely. So I think what we've got is a couple of easy explanations. Of course, those small holes, or maybe the big hole that you have up on the upper right there,
right,
that's a result of actually self-healing.
Okay.
So that's the vaporization, as you'd expect. Now, when we start getting into the other area, we could explain things kind of easily. As you roll this thing out from the left to right or right to left, you've noticed that there's a variance. Some of that variance is due to the difference in the connectivity from the shoopage on the termination to the actual electrode. So at one point in the video, you showed a very light background with some speckled scenarios, and that was just moisture in a high resistance scenario. But what we're seeing here is in the crack lines, the lightning bolt looking thing.
Yeah, that goes right. That almost went through the whole thing.
Yes, that's right. So I think what you're doing, you're having this this reaction of the moisture, and what's occurring is that you're getting a moisture effect that's actually causing the electrodes to change. They're getting more resistive. They're getting some migration or movement, oxidations, changing resistances. So those voids are most likely, to some extent, like a micro healing or a impulse degradation. That's how I'd explain that lighter center section. And the darker blotches are most likely a result. Yes. Yeah, those are going to be most likely a result of end termination corona type effects, something on that order. So it's always difficult to comment, maybe 15, 20,000 miles away or so. But and not having dealt with the parts. But I think that's pretty much the scenario. It's definitely a moisture event.
So will the moisture eat away at the metal? Will it actually corrode the metal? And what sort of metal are we talking about here for the metallization layers?
Well, in some cases there's zinc, but this most likely is not the case. It's usually alumina. It's probably on the order of 100 angstroms. The dielectric thickness itself, so the film itself, is probably in the order of maybe 1 to 20 microns, something like that. So it's a wonderful part when they work well, and I suppose it worked in a sense.
It worked. Well, this one is only a year old. See, that's the thing. That's why, because when I think of moisture ingress, all I think of is like old school reefer paper capacitors, which are famous for, getting moisture ingress. They crack, the cases crack, moisture gets in, it is absorbed by the paper, and then when you go switch it on, you've got this big conductive path that just goes boom, and the magic smoke escapes. I just didn't expect that moisture ingress with film caps after like a year. The actual product it came from is only a year old. Yeah,
I can make a couple of guesses on where the moisture came in, and that's a big issue. Choosing the right epoxy is tough, and I'm sure these guys build great capacitors. It could happen to anyone, but the right material systems, it's a real secret, right?
Yeah, and is that something you can test like after you've constructed them?
Yes, that's a very good point. So
how do you do that?
What we could do, we'd put them on a moisture humidity test. Maybe it would be good to have 40 degrees C and 40% RH, and maybe another 40 degrees C and an 80% RH relative humidity cell, and then do an 85-85 cell. And what we would look at the degradation of capacitance across time, and that would tell us a lot of things about what's happening within the device. Then we'd probably go in with EDX, and we would do some X-ray evaluations of where the material systems have broken down and constituency of water, etc.
And you're not the only one with this opinion as well. Tom Zednik, if I'm pronouncing that correctly, who's a former colleague of yours from AVX, who's now over at EU Passive Components EU. He's also of the same opinion that this is a moisture ingress problem and not really an impulse. Because as you said, some of those small little points in there might be self-healing. Is that certain? Is that the size of hole you'd expect from self-healing as from an impulse thing?
Yes. Yeah, it's pretty neat too to throw these on a sample scope and apply a couple of different signals to them, and you'd actually see some noise occurring when we have self-healing events. So that'd be a neat,
noise. What sort of noise are you talking about?
Well, you'd actually, apply maybe full voltage at maybe a moderately high temperature, and you might actually see some failures punching through, and you'd actually see some variation in the applied voltage of the part as this thing coronas. So when you get those little micro healing points, you actually vaporize that electrode material, and as it cools, it precipitates around that failure site. So if we could blow this up a little bit more with a SEM or something like that, we actually see a little dark halo around that white point of failures.
I might put this under the microscope and see if I can see that. So this large hole here, I don't think that's a self-healing blowhole, would it? Would you get one that large?
Well, you could. It depends what hits it. I think that's maybe more unlikely.
Maybe I've torn it there? Is it possible that I've torn this when I've taken it apart? Yeah,
I think you did a good job on the DPA, but I think we might have approached it a little bit differently.
Right, okay. Well, it was my first time, okay.
Oh, you did good. We'd still hire you.
All right, all right, good.
One of the things there, though, is there's also a possibility, unlikely possibility, but there's a possibility that the metallization come off of the film.
Right.
So if you had the counterpart of that roll, you could see if that was a deposit.
I think I did see that as I was unrolling. It looked like some of them peeled apart. So yeah, I wasn't sure if I had the correct layers or whatever peeled. So yeah, I wasn't really.
It's hard to do.
Are there like qualified parts that would be better qualified for moisture ingress? Like, do you sell, for example, higher quality ones that are better? Like, look, we guarantee these ones are hermetically sealed and you won't get moisture in?
Well, we don't have hermetically sealed films from what I know.
Right.
I don't know that there are any. Well, I almost take that back. There's films in cans, so okay, they're hermetic.
Okay.
But they're a much different application. But I think in reality, some of the progress that's been made on the encapsulants could get you such a near hermetic case that you would never experience this.
Right. So if it's in a metal can, that's by definition hermetic, is it? If it's welded? If it's a welded can?
Many companies will take great care in ensuring the atmosphere within that device. Yes.
I don't think I've ever seen a metal can film capacitor. Is there such a thing?
Yeah, there is. So I mean, some of these guys are
the bigger ones. Oh, right, the big bad boys. Okay,
yeah.
right.
And we made them about the size of half of a Foster can. But,
right. You're right.
Not surface mount though.
Okay, got it. So when you, like the ones that we tore down here, where's the seal-in point? Is it the potting? Is it when they potted? Is that what they're trying to do? Is that they're trying to seal it as best they can?
Yes.
Or, right, yeah, okay, so if the potting's poor...
Yes. It would possibly be at the perimeter of the metallization to the encapsulant.
Right, okay. And then through the shoopage on the side, really. It'd come in through the side. It wouldn't come in through the actual film wrap, would it? Because I would imagine that's pretty sealed.
It's correct. That's correct.
Right.
It would be at the interface of shoopage or some errors or voids in shoopage.
Got it. Okay. Well, we've got a failure modes document. Failure modes. I can't zoom that up, but I can put an overlay up here. So this actually shows the failure modes, doesn't it? Or the most likely failure modes in sequence.
Yeah, there's some good information there. I think possibly the snapshot of the fuse areas or the other one that showed the punch through is a good way to look at it. Generally speaking, you could say there's two types of films. There's the smaller, low-power films, and they're dealing with that thin metallization on the dielectric. So we've got maybe 100 microns. And in small scenarios, we'll have a punch-through, we'll have the cooling of that vaporized metal, and it heals, and we drop cap a little bit. So that's one case. And then when we get to very high-power films, there's actually microfuses that multiple companies put on their product. So normally you'd think that maybe scribing fuses, and here we go, on the bottom part of number 4, you could see that there's tiny electrodes and little connections between those electrodes.
Right. So a little grid, a little square pattern, a little square boxes with little conductive parts between them. Okay.
Yes. And the trick is going to be to make sure that those fuses don't die under certain use scenarios of the film. And now that's more common with the really big films, the ones that are maybe, 20 kilowatt drives or something like that.
Right. So you wouldn't find those on little surface mount jobbies or the small ones for mains and things like that?
They could be, but I don't think that anyone has that.
For the application that we're looking at here, which is like a capacitive dropper kind of thing to power a circuit, which you probably apparently shouldn't use X-class caps in this situation. Is that something that you are familiar with?
That. Yeah.
Okay.
You might be able to get away with it.
Right.
I'm kind of surprised about the failure. Usually films are incredibly reliable. Now, their disadvantage is that they're quite large on a relative basis for the amount of cap you get. But, of course, the self-healing and some of the other low-noise characteristics greatly outweigh that.
Right. So is moisture the most probable failure mode? Because apparently if you're in the industry, there's other YouTubers out there who tear apart, these cheap Chinese little, $5 gadgets, and these caps just fail all the time. Is it most likely to be a moisture problem causing this, or a capacitance loss due to impulses and self-healing?
Within films, it's difficult because if you don't get self-healing correctly, it could very well have an early failure. So that's something to be cautious of. Usually the industry is getting much better with that. I would say in the old days it was well over half being caused by that early wear out. I think it's probably switched Yeah, so it's probably moisture.
Probably moisture. There you go. I thought it was only the reefer caps that had moisture problems, and a year into it too, just a year-old product. I just thought, wow, and it's losing so much capacitance. So it just eats away the metallization layers and causes a drastic drop in capacitance, which then, of course, if you're using it as a capacitive dropper, that changes the value and that screws up your circuit.
Yeah, that's right.
Completely. So, yeah. Awesome. All right. Well, thank you very much. Ron, that's something I went into this video thinking that it was an impulse self-healing issue due to capacitance, but it looks like it's probably a manufacturing moisture ingress type issue. So there you go.
Right. Hey, and I'll tell you, Dave, if we have a failed cap, one of these big power caps, that are about the size of a file cabinet, it's 100 kilograms.
Oh,
and if they're out on the Asia and such, I'll be able to ship one to you if you want one. Sometimes they're dented.
Right. Yeah. But it'd have to be shipped by boat. It'll have to be shipped by the slow boat. They physically ship by the slow boat because you can't put them on the plane. Yeah. Wow.
Yeah. We're in CERN and stuff like that. So, like in CERN, when we start getting into concerns or other power drives, right? We can't have a compressor go down because of a failed cap. That's where those really big guys are used.
Right. Okay. And these are all would these be made to order? Or whatever, like these giant ones?
Yeah, they are. I mean, some of them are like 75 kV, massive amounts of energy. Of course, you can do directed energy and some things like that. But the little guys, they kind of come off of a bicycle wheel that has the film wound around it, and then they're just cut in a certain arc.
Right.
Then they're put into a frame, they do the shoopage, and, we're done.
So what is the shoopage material that you guys use mostly? Or does it vary? Or is it a secret sauce?
I think there's part of that too, and most of I've forgotten, so it's difficult. Right. I have to admit, though, I've done that on many years ago when we were experiencing some different material systems.
Okay.
We're actually trying to shoop upon glass for a variety of things. But that's made a lot of progress through the years. It's interesting, though. So shoopage might have they might go 0.8 millimeters or a millimeter in.
Yeah.
And other, just to put it in perspective, right? So some of the other accuracies on our processes, not films, but other types of caps are 1 micron line width. So that's, it's getting down there, right? And then if we look at the thickness for a high CV ceramic capacitor, well, some of those might be 0.4 micron particles and 2 micron dielectric thickness. So a lot's been going on in the world of caps. Right?
Yep. Oh, it's phenomenal. The variety of caps it's just dozens and dozens and dozens of them. It's just incredible. So can you take us through some of the technology?
I think this one's kind of neat because it shows, we went from the bigger caps. Remember in my early career, I remember we couldn't put a 0.1 and a 1210. And,
right.
That's amazing, right?
Yeah. So that's 0.1 microfarads, folks.
Right, 0.1 microfarads.
In a 1210 size capacitor. That
was the old days.
And we're talking imperial here, not the new metric sizes either.
So now we could do that 0.1 in an 00804 or an 01005 if we want to talk a big part, right?
I don't even know what that size is. I mean, it's so ridiculously small.
Oh, it's teeny. In fact, we could do 1 mic in an 0105. It's under development. So, what's happened?
1 microfarad.
It's hard to believe, isn't it? Yeah. So
crazy.
The miniaturized parts are really a huge impact on everything.
But you pay a penalty for that, don't you? In the dielectric you have to use, and the performance is absolutely terrible, isn't it? There's no way you can get a quality performance dielectric that small with that high a capacitance.
Right. It's not going to be stable with temperature or with applied voltage or with time. Yeah, even some AC noise on that, some ripple. Right.
Oh, right. Yep.
But
So-
yeah, it's amazing what's been going on there.
So-
There's a low inductance aspect
Yeah.
to this as well. When we look at the old days, maybe a 1206 was a nanohenry of inductance. And now the 0204 might be 120 picohenries. But there's other termination mechanisms where we're terminating on the side, so we terminate on the long length, and the electrodes are perpendicular to the board, so we have a very low loop inductance.
Right.
And, we could get inductances of a capacitor down to maybe about maybe 25 to 40 picohenries.
Wow.
And of course,
That's insane. That's just crazy. You would get more on your tracers going to the component on your PCB than in the cap.
Yeah, you have to be really careful.
Yeah.
Because you could mess up a very highly performing cap with a bad layout.
A bad layout. Yeah, exactly.
I mean, it does so much for you in terms of the resonant point and the ability to supply high DIDTs to so many different types of circuits. We might be doing low side drivers on LiDAR. We might be FPGAs, etc. But a lot of work has occurred in the material stability.
And is that what this is showing here, the stability?
Yeah, what we have is there's some DC biases. They vary by dielectric type. They actually vary by lot as well. So engineers should be very cautious. Yes.
Okay, right. Okay, so one product may not perform the same as the one next month because it's a different lot. If you don't design it,
true.
if you don't, if you're working in such a critical application where that matters.
Yes, or you could contact the manufacturer, and we take these questions every day,
Right.
and we give you certain series within high cap dielectrics, which are stable. And on the right, you can see how much it varies by manufacturer. Now, and this comes from EPCI, European Passive Components Institute. That's Dr. Zednichik's site. He's done a great job in showing the overall performance of some of the key players. And you can see the variance is just major.
Yeah.
But as we said, if you take care, talk to the manufacturer, you could choose the right one that's going to greatly minimize changes on a lot by lot basis.
Especially if you're on the high performance aspect side of things, choosing the absolute, and there's where you can't change brands, you can't change supplies, like even batches might have a problem. You might have to select on test even, perhaps.
Well, if you were careful and talk to the manufacturer, you're safe.
Okay, got it. Yeah.
And you can see here, we're looking at the various amounts of variance because of ripple on dielectrics. That gets significant. So it's quite possible that if you're not aware of the phenomena of the dielectric instability with bias voltage and temperature and time, you might think you have maybe a 1 mic part and you're down to 150 or 200 microfarads.
Yeah, that's a real big deal. So what is the latest, greatest dielectric? Is it like that gives you the highest volumetric capacitance per unit size?
Well, great progress has been made in the ceramic world. So particularly now that AVX is part of Kyocera, the Kyocera group has a very big stability effort going on. They've made some tremendous material changes there in ceramics. So that's really important. And that's going to occur across the world. I mean, as manufacturers, we know that we have to have more stable ultra-miniature parts. If we start looking at other types of dielectrics, and of course dielectrics are everything in terms of cap performance.
Yes.
We could talk about the tantalum polymers. They have a lower ESR. It's approximately, you could argue, it's about 1/8 of a traditional MnO2 tantalum. So that allows us to get about 8 times more current.
Right.
And
wow.
The great thing about that is they're incredibly stable. So that's a big deal. And then in the world of supercaps, well, we could give you 1 farad part in something that's maybe 6 millimeters in diameter, about 9 or 10 millimeters high.
That's crazy. What at what voltage? Like 3 volts or something?
Yeah, about 3. Yeah.
Right.
Yeah. Now those you want to derate. So
Right,
every time
okay.
you go up by 10 degrees C, you have
Yeah,
to
yeah.
light. And every time you go up by like 0.1 volt, you have to light. And this
Sorry,
is
did you say
interesting.
every time you go up 0.1 volts, you halve the life?
Yeah, roughly
Point
speaking. Yeah,
one.
there's a great paper on that. Yeah. Yeah.
I'd
Well,
love to
it's
see
a
the
good
curve
life
on
to
that
start
before.
with, though. Yeah, there's a good life to start with, though.
Oh, wow.
Yeah, but in fact, though, there's a lot of those in vehicles now, whether it be our dashboards or the dying gas on your emergency call circuits and things like that. It's really interesting.
Is that to keep like emergency power there, just in case the electrical systems fail and
Well, yes.
something?
In the
Or
case of the e-call, it's used for backup, so you can get that one call. I've had an accident at whatever milepost.
right? Yep.
And for the case of there's an interesting case on some of the trucks here in the States. There's an inverter, and that inverter has a buffer with a large supercap that goes essentially to the alternator. So as you plug in some oversized saw like everyone does, and I'm guilty of, you don't cause problems down the line.
Right.
Yeah.
Got it.
Hey, but this slide is really neat.
Yeah.
Because it talks about
These are tandem. These polymer tantalums. Yep. These aren't your old school daddy tantalums that blow up.
No.
These are well. Is there still a flame issue with these types of
No.
polymer
the
tantalums? Right.
polymers, they're all benign.
Yep.
Yeah.
Okay. Very good.
They're incredibly good inductance and great stability. So these are going to be solid as a rock. And what we've seen is many times you're going to want this bulk cap that's stable, low inductance, and all of that. So you use this in conjunction with some of those high CV, less stability ceramics. So you'll see this around all of FPGAs and some cores and things like that. There's the low inductance stuff.
Tell us about how you minimize inductance by case size.
Yes, what we try. Well, of course, as you go with a smaller case size, as you can see, the first column shows 1206 all the way down to 0201. We drop the inductance, as you'd imagine. That's because we have a lower loop area for the end terminations. So the next slide over is called the LICC, and that's where we just terminate on the long end.
Yep.
So we could drop the inductance by a factor 2. And then there's a device that looks like a cap array, I believe. I'm not sure if we have a slide on that. But yeah, there we go.
Yeah,
Okay,
there we
so
go.
We further
Yep.
drop. Yep. And the last one looks like an LICC.
Yep.
So
this one here is 4. Is this 4 caps in one?
No, that's a good
No.
point. It looks like a cap array.
Yeah, it does
it
look
isn't.
like a cap array. Right. Okay.
Yeah. What we've done there is we've just put alternate terminations on the part. So
Oh.
you have essentially a single part with 4 terminations on it. Yeah. Hey, now it's interesting too. I could get you a free AVX Capacitor AVX shirt if you guess the number. On a 1206, how many IOs could we put on it in theory?
A 1206. How many pins you talking about?
How many pins? Yeah, how many land grid array pads could we put on it?
On a 1206, point. Hang on.
Don't guess now. You're gonna make me feel bad.
An 8 per side? No, it's
Nope.
more than that. A 12 per side.
We could do 32 on the bottom side of the package. Yeah, so you never want to use that. But the point is that the metallization accuracy is so good that putting 8 or even 10 isn't that big a deal. So I think
Wow.
we've got further reductions coming in low inductance. And I'm a big fan of land grid array caps.
Right.
And in the world of RF, it has a lot of advantages where we could drop parasitics.
So what is the difference between the array one, the pin array like this, and just the one big strip like that? I would have thought this would have been better.
It depends on the case size. So in if we look at like an 0603, the standard 0603 part would be about, let's say, 450 picohenries. So in the LICC, this part, or excuse me, this looks like an LICC, but it isn't. That's going to be on the order of about a couple hundred. And maybe you could say, I don't know, 110 or so on the best. But this land grid array part, the part that has the vertical electrodes, that's about 30 picohenries, maybe 35. Okay. Yeah, so now the trick there is that we have the electrodes vertical to the board. Mm-hmm. And in the RF world, I don't know if you played around with a lot of ham radio stuff, but
I'm not an RF guy, no.
Well, all us cheap guys will take a bad capacitor. At least before I worked here, and they gave us free caps to experiment.
Yeah.
What we do is we take a cheaper cap and place it vertical on the board, and you'll get a better frequency response. So you naturally reduce the inductance that way.
Right. So you'd flip your SMD part up on its end. Right.
Yes.
And you'd get better.
Only certain case sizes. Right.
Oh yeah.
Yeah, but when the math works out and it doesn't fall over, it's a good solution. Yeah.
Oh, terrific. Or you'd put multiple ones in parallel on the same pad vertically?
Yeah, you could do it. In fact, that's a good point. There are larger case sizes, and in fact, there's a new military spec coming out that allows the manufacturers worldwide, capacitors, to take capacitors and put them vertically or horizontally in between a lead frame, and now you have a very low ESR, low inductance bulk cap.
Right.
So a lot of those are flight systems.
Ooh. Would you know this? It'd probably be in the sales department or something, but what is the most popular size these days, like in volume? What would you make most of? Like in terms of just a regular SMD ceramic cap? What would
I don't think it would be any larger than an 0402. It's probably an 0201.
Right, an 0201. Oh, is that probably driven by the mobile phone market, I guess? Or
I think it would be.
Driven,
yeah. Right. Now, in fact, I get lucky because I get work on many different programs per day. And we were dealing with a satellite company looking to do an 0201 flight cap. So they're not yet at that point as an industry. But I'd say 0402 would be the realistic spacecraft limit.
Okay. Is that because the smaller you get, the less qualified you can make them, I guess? The less, like the more vulnerability you have in terms of physical variation and physical failure modes?
That's pretty true. Yeah, it's good intuition. So what happens is when you think of this part, if we were to do a cross section, think of vertical electrodes or chunks of metal that have to be isolated from the outside world and moisture, right?
Yeah.
Because of the effects it would have on it.
So even in ceramic caps, you have moisture issues. You can have moisture issues as well in ceramic parts.
In here,
right?
Moisture would we drop our insulation resistance, and then we'd have a problem. Hey, but by the way, there's parts that have terminations that have a submetallization of a conductive epoxy. And that conductive epoxy, it will actually allow you to bend the printed circuit board and not have a crack propagate in the cap. Multiple manufacturers have it.
Yep.
It's a really big deal.
And yeah, well, I've done, this is, I think, the next slide. I've done a video on this and ceramic capacitor cracking and board flexing and how this can cause shorts and fires. I've had my own products catch on fire because of, the board is flexed. And, people mount them. It's also a PCB construction, PCB layout thing. If you put it too near to a screw point, for example, like a mounting point, for example, just screwing in your board into your chassis can cause a crack in your capacitor and boom, up it goes. Or
it could be a disaster.
Yep.
Yeah, and especially on a car. Imagine like terminal 30 powered all time. Boy, you got real trouble.
Shock and vibration is crazy business. Is it mostly shock, or can you get cracks through vibration as well? I'd assume that's less common than shock impacts.
That is true, but there's actually a paper that I believe was done by NASA that talked about a vibration-induced crack. It's very uncommon, in fact. Hey, but it's interesting. Most of the failures on a capacitor, ceramic capacitor specifically, are application errors. And so if we took, let's say, a million failures, right, or something like that, I bet maybe less than 10, no, goodness, less than that. It would be less than, we got to look at maybe 100 million caps. so maybe one is the manufacturing error, and the rest of them usually are mechanical issues.
Right.
It's amazing, the percentage. It really is.
Wow. Yeah, well, I'm stunned that you can even make them this small, or I'm stunned that anyone would want to use ones this this small. But I guess you have to, right? That's the progress. But as you said, certain applications, military and space, or airlines or something like that, they're very on the safe side. So they're going, oh yeah, we'll use these 0201s, but I don't know. Seems a bit like, yeah.
Right.
I guess it takes years for them to qualify.
Well, it does. Yes, it does. And if we look at a comparison between a flight part and the highest capacitance, high CV part, you could probably say the dielectric is 4 times thicker on the high rail part.
Wow.
So now lots changing, and it'll continue to change. Particle sizes of the ceramic are going to get smaller, so we'll have less E field per grain, things like that. But for the most part, there's going to be some practical limit where we're not going to really go underneath it. I thought it might have been 0201. Certainly it isn't. And maybe I'll bet that there's one more iteration after 0105.
Right. Can you explain? You mentioned E field per grain there. Can you explain what that is?
Yeah, if we look at, I should have given you a better diagram.
Do we have anything
if we looked
else?
in between the electrodes, we would actually see the grains almost stacked up between them. And what you'd like is maybe X number of grains, so you could divide the electric field across each grain. And if one fails, you don't.
What actual material grain are we talking about, though?
Barium titanate, so it's a ceramic grain.
Okay. Right, so they're actually, they're granular? At the physical level, they're actually a granular structure?
Yes. Yeah.
Oh, interesting. I assume.
That are fired into a monolithic block. And the grain sizes are usually on the order of about, it varies there again by manufacturer, composition, but we could say maybe a half micron or so.
Mm-hmm. Interesting. Yeah, I always just assumed it would be a solid ceramic material, but you're saying it's grains compressed.
Yes.
Okay, right. Wow, that's something I didn't know.
It's really neat. So we build this by taking ceramic, milling that ceramic to a certain particle size, and then suspending it in a binder, so it almost looks like paint. And then we'll pour that paint out on a stacking mechanism, and then we will dry it. We'll put a liquid metal, a liquid electrode on it, and then do the next layer of liquid paint, that dielectric, and then do the opposing electrode, build up to the right cap value and XYZ thickness. Yeah.
Wow.
It's really interesting. It's basically a liquid cap.
How do you produce like billions of capacitors? I don't know what volume just AVX would make every year, but it's got to be in the billions and tens of billions of capacitors. It's got to be. Right. It's crazy, and you can buy them for next to nothing. Well, not the real high value ones are quite expensive these days, but like just a jelly bean low end one is just so cheap.
That's true. So much has occurred in terms of the mechanization on this, and it makes sense. We got exceptionally good, built our own equipment, came up with special processes, so the selects are exceptionally high, and you could kind of see why, given that volume. If we make an error, it's repeated very quickly.
Right. Yeah, if somebody tweaks something on the production line that they weren't supposed to, right. Okay.
It's very cautious, very stable.
Right. Is it like, are there many people on the production line? Is it like or is it like as completely automated as you can get it?
Well, it's not like a resistor factory. I've had a chance to see one. And I believe they were building 1 billion plus with, I want to say 8 or 10 people. So we're nowhere near that.
Okay,
But,
right.
but it's not an army of people.
Wow, that's incredible. So what are the different technologies for the, you've got FlexiSafe trademark, but
Yes.
I'm sure you do different techniques for flexible end caps. This is what I've talked about in my video. It'll take so as the board
Yes.
flexes, like that, then the capacitor, then the end terminations can decouple that stress from the ceramic.
That's right. Yeah.
You've got different techniques for that?
We do. Now, it's stabilized to one material system, and it's a great trade secret, but it basically
Right.
has a conductive epoxy. And that could be very problematic because if it's not the right conductivity, we increase the ESR.
I was going to say, yeah, you screw up your ESR, yeah.
Right.
And does that
Right,
mean
so
your ESR can change slightly when it flexes?
Well, no. We're
No?
very cautious. It
Okay,
could.
right.
That's a
It
question
could in
to
theory.
look at for an
Yeah.
end user. Right.
Right.
And the other one is ESR could change, and suddenly you can get a short if that conductive epoxy is I want to say it without giving out trade secret. If it's the wrong
Okay.
conductive epoxy.
Right, okay.
Right.
No, it's
So you
all
have to
good.
be very cautious. And I'll have to say that the flexible terminations have gotten very good because there is a military spec,
Right.
32535, and they actually call out the use of flexi-term or flexible termination material sets.
Got it.
And there's multiple suppliers to that. So it's
Yep.
But truly, as end users, they should be careful to make sure that termination is stable with ESR and under environmental conditions.
Yes. Yep. And there's on the design side of things, as a designer, you can, if that's an ultra critical spot and you can't afford a short in a capacitor, then you would put 2 in series. You halve your
Yes, that's right.
capacitance, but it improves your reliability.
And that's
So-
what we're looking at here. This
Yep.
FlexiSafe has the 2 caps in series. So this is the traditional.
Oh yeah,
thermal
I think we
30
saw that.
solution.
Yeah. Two caps in series there. Yep. Okay.
And the
Right. So
flexi
that's
term is
that's
the one.
built in. So you don't have to do that on
Yes.
you don't have to use 2 parts on the board level.
Right.
Yep.
And here we're showing the ESL of 2 parts in series versus a single. Of course, the
Right.
value on the FlexiSafe is half, as you said.
Yes.
And then
Right.
we did a frequency plot looking at ESR, and
Yep.
it's
There it
very
is.
appealing.
Yep. Terrific. They'd also use those in the automotive market too, wouldn't they?
Yeah,
I
critical
would
data,
assume.
self-driving technology.
Yep.
Right.
Yep. There's rumors going around that because of the component shortage in the automotive industry, they're putting in dodgy caps instead, like they're putting in non-flex ones instead of flex. Anyway,
Well, I don't know.
that's just a rumor. So
Maybe
Yeah.
I don't. I'm kind of far out of that.
yeah, no, I'm sure.
like-
No, I don't expect a comment from AVX on that. That's not your.
Yeah.
You just sell them. You don't actually
Yeah.
implement
I know
them.
our guys would love to take the orders.
Yeah, right.
Yeah. It's
Well,
classic,
is
though,
it-
well, I was just saying about lead times. I don't get involved in lead times, but I just wasn't aware there was any problems. But so much is going on. The usage is off the chart.
Oh yeah, well there was was it 5 years ago now was the great capacitor shortage? That was nuts. Is that because there was like one or two one factory caught on fire? I can't remember the details of that.
I don't
was-
really know.
Oh, it was bad. You could not get a reel of SMD 1 mic caps to it didn't matter how much you paid, you just couldn't get them at one point.
Yeah.
And it was
I know we've expanded beyond belief. And,
Right.
and that's great.
Okay.
So, I think I'm badge number 4 or 500, right? And I think now the company's at 28 or 30,000. At least our division of KSR.
wow. Yeah, yeah.
It's grown.
That's nuts.
Yeah. Right.
So
it is.
right. So what's this pulse withstanding stuff?
Yeah.
Can you explain
Well,
what makes it a pulse withstanding? I mean, we're talking 24 kilovolts, 26 kilovolts, 28, 30.
Yeah,
Wow.
pretty significant stuff, right?
Yeah.
So when people want to, we realize 2 things, right? Number one, we build a varistor, which looks like a ceramic capacitor, but in the presence of an electric field, it will become conductive. And it's just like the big old MOVs that you used to use on 110, right?
Right.
But now we can build them down to an 0.201 size. They don't wear out and all of that. But the pulse withstanding caps, when you want to integrate versus clamp, these are ceramics that are used on less sensitive IOs that if you integrate down to a few hundred volts, the IC will survive. So this is a big deal.
Right.
A lot of times we used to pray, right? In the old days,
Yeah.
10,
Exactly.
500 volt part. You know.
Yeah. Okay, but these are specifically engineered to do this
Absolutely.
job. What else? Low inductance, high current jobbies.
Yeah. Well, you know what we did? These are 3 terminal caps.
Yeah.
And now there's a 10 microfarad, I think a 15 microfarad 0402. And what happens is we've made this into like a T filter. The next slide kind of shows what's occurred.
Yep, there we go.
And basically what we've done is we take out the parallel inductance, looking at that equivalent model. So we have a low cap C1 to ground, low inductance, and that's thing that could be 10 or 15 microfarads. And then we'll inject or transform that parallel cap into series cap inductance.
Right.
So we transform the parallel inductance to series. And we end up with a very low Q filter. So that means it's broadband. You could be 30 dB down across maybe a gigahertz.
Right.
And you could start that response at maybe, 20 megs. And you could have, depending on which part you choose, you could have parts that have their endpoint 30 dB points at maybe 10 gigs. So it's a neat, cheap, dirty broadband filter.
Got it. And it saves board space too, which is,
Oh, it does. Right. And it
always
takes a lot of the questions out of like hysteresis on the inductor or temperature fix on the inductor, etc.
Got it. That's all taken care of in the part. You don't have to worry about component selection there for your capacitor and your inductor and everything else. It just makes the design process vastly easier. So well, there's some of the benefits there. Yeah. Nice.
Just real easy to use. And actually, that's out of date now that we can do up to 10 or 15 mics. But, it's kind of interesting. But it's easy. You can see the response, and they're kind of interesting. All of this has SPICE and simulations that are exportable. And of course, all the manufacturers are putting out much more SPICE models, of course.
Now you're a capacitor manufacturing guy rather than a electronics design engineer. Actually, what is your background?
Double E, yeah.
Yep,
so
double E.
I
Okay.
Come here rather than doing design, but
right.
might be able to do a couple things. I don't know.
Okay. What's your standpoint on multiple caps in parallel for bypassing? Because there's a ton of people say that just one big 10 mic jobby is fine, because that's what these impedance curves here. You overlay 2 impedance curves and you're supposed to get a broader, lower impedance path over a wider frequency range if you use 2 caps as opposed to 1.
Certainly that's true. And we've seen that as a trend, and seen people that want minimum ESRs and controlled ESRs for ringing and all that. What's interesting is that the low inductance parts, the LICC, the LGAs, the ones that we saw before, those kind of change things a little bit, where you might be able to use a big bulk cap in one of those. Now the 3 terminal caps, this feed through concept, it changed things a little bit further, because you might have a 10 microfarad cap, but it has a very low inductance. So it has a broad frequency of operation. So although it's very valid to have the multiple caps in parallel, and of course there's negatives to that, right?
Yes, it can. Poles and zeros with your PCB inductance, and it resonates to buggery, and
simulation kind of helps you out, but the effort was put into on the low inductance parts, LACC, LGA, and then now this 3 terminal cap. I think we're starting to change things. And there's something that we can't really talk about, but imagine a true bulk capacitor that has a feed-through characteristic. So that'll be something that it'll be coming out soon.
New capacitor type. Okay. Exciting. Specifically for bypass applications?
A lot of applications.
Right. Okay. Right. I'm sure there's many. Yeah. Right.
But
Okay.
yeah, it's kind of interesting. But it comes back to the metallization control and the material advances that are occurring. There's a lot of those trends which are reinforcing one another.
Yep.
And it's really going to provide some significant new types of components out there.
No, that's the shock vibration, anti-shock vibration stuff. Yep.
Yeah. So the terminations on the tantalums tend to take quite a bit of stress. And in fact, one of the best applications for tantalums now, well, there's great applications. One is on SSDs to hold up, the die and gasp there.
Right, okay.
But then, with everything we learned there, we took a relatively standard tantalum, the MNL2 technology commonly, and they could be a great part for wake-up caps or even low-level scavenging energy harvesting caps. So ILT is seeing a big use or potential use of ultra-low leakage tantalums, small package, quite good.
That's interesting because I never associate low leakage with tantalums. That's something like as an older guy, I just don't associate.
Yeah. Well, me neither until I saw the curve. In fact, after this, I'll send you the curve.
Yes,
and
please.
It's amazing. If you derate, it's exponentially dropping.
So that is the trick, is it, to derate them, and then the leakage. Right. There you go.
Yeah. The other neat one is on tantalums. The bathtub curve. Okay, it's true, but the end curve is maybe 1,000 years out or so.
Right, okay.
So, they're incredibly reliable parts.
Wow. Okay. Yeah, because they got a bad rep, especially the tag tantalums. The old school tag parts with the through-hole pins and just the blob types, which are famous for catching on fire and whatnot.
Yeah. Well, they actually could self-heal to some extent.
Oh, okay.
Yeah, and that's why we tend to derate them. So, in fact, I have a neat spacecraft story. There's a device that's flying with a tantalum that was installed incorrectly.
Oh, no, backwards?
Yes, sir, yeah. It's like a 1-point rail, and I think it's a 50-volt part. So, it's not recommended, of course. But there's some, I guess, horror stories in production that kind of turned out well,
Right. So we can't name this probe, can we?
No.
No. Okay. Right. Okay. Is the probe or is it a satellite? Can we narrow it down?
I can't hear you, Dave.
Okay. Okay. All right.
Yeah. I can't actually say for sure it's our part. I don't know, but I was involved on the meetings. And it was amazing. It was a great thing to attend.
Oh, that's great. So what, did it die?
No, it's fine.
No, it's still fine, even though they installed it backwards.
Yeah, but the derating is so massive.
Oh,
right?
okay.
So
it's so right.
50-volt part in space that's already saying it's it's a much higher voltage that we derated to 50, and they derated it to like 1 point, whatever.
So that was part of the design process. It wasn't just luck that somebody spec'd in a higher voltage part. They deliberately derated it, and that came in handy.
Yes, it came in handy. Yeah, that's right. It's really handy. That's kind of an extreme number of derating, wasn't it? But,
yeah, right. Yeah. Oh, wow, that's terrific. And this shows the internal construction of those. Wow, is that like a little pin in there?
Yeah.
Is that like it's got a little wire?
It's got wire.
Right.
Yeah. So tantalum wire is we kind of start with some length of that, then we press a pill around that, and then we basically process the thing after that. So you've got essentially a tantalum plug which is porous, right? And then the wire is going to be your other end of that. Will basically form a very thin dielectric through an electrochemical reaction, and then we'll put on a counter electrode. And the counter electrode is kind of where you get the ESR, and that's where the conductive epoxy makes a big difference. I don't think tantalums are going away at all. And I think tantalum polymers are going to have a lot of growth. They're going to do really well.
Right. Yeah. So what's the biggest usage case for tantalum polymers as opposed to MLs. When would you want to use a tantalum instead of a whiz-bang 100 mic multi-layer ceramic cap?
Well, stability. You're always going to get stability, and I think ultimately
You're
I would
talking
probably go as
voltage.
far-
You're talking voltage stability, temperature stability.
Yes.
Yeah,
Time,
right.
All of that.
Time.
Yes.
Right. All of it. Yeah.
Yeah, and now incidentally, the tantalum polymer has just had a military spec come out, 32700. So that kind of reinforces the known and proven history and reliability of the 55365 military tantalums and flight tantalums. So, these can now be even quite high reliability devices. But the amount of cap you can get in there is quite startling. So in the commercial world, the tantalum polymers are great for the things like, I don't know, it might be the SSD drives.
Yep.
Tantalums or even tantalum polymers are ideal on the negative gate bias on HEMPs and VDD lines, where you don't want to have a bigger electrolytic.
Yep. Got it.
Electrolytics are fine; they could work there, but
Yep.
the tantalums are a much smaller package and also much more reliable. So
yeah.
you'll see
Okay.
a lot of these in flake.
Is that because of the sealing you can get in them?
Right.
In the packaging instead of like a metal can sort of like plugged, because they're plugged from the bottom or whatever.
Yeah, that's partly true. So we got electrolytics too, and the real trick, as you say, is in the wet electrolytic is to seal that can around the bottom of it. There's a seal, and of course the possibility for that thing to go bad.
Yep.
So that's a negative on aluminum electrolytics. Of course, there's hybrid electrolytics and polymer aluminum electrolytics that get rid of those issues. But the tantalum is also inherently more reliable than the aluminum electrolytic system.
Right.
And it's funny too. Everybody calls them tantalums, but really they're also an electrolytic.
Right. Yes. Okay. Yep. Gotcha. This looks difficult to manufacture. This looks tedious, I guess, to manufacture.
Well,
More tedious than any other type.
Yeah, you got that electrochemical reaction, and it's also well controlled and easy to put these out in the billions, I think.
Oh, okay.
In fact, I think there's a YouTube video on our process.
Oh, really? Oh, okay. I'll have to try and find that and link it in. Yep.
I'll try to find it for you too.
Yeah, that'd be great. Yeah. Okay, so tantalums are, tantalums are the in thing, huh?
Well, it is, and a lot of the FPGA and the real high-end processors, they're going to be using this technology because it's low inductance. It's inherently lower than the aluminum electrolytic. You could also, with the multiple case sizes, you have a lot more ease of being close to the processor, easier layout, things like that. The stability and the ESR is a great advantage. So, there's a lot of growth. It's funny because I could almost say that in the world of semiconductors, passives can tend to limit the semiconductors' end performance. In fact, I can give you true examples of that. So it's becoming quite important that you're using the right passive.
Right. So would anyone use a wet electrolytic for bypassing these days? I can't see why you would. For bypassing
I think because of cost.
So, okay. It's going to be less than a tant, I guess, if you need like 100 mic in, 10 volts or something maybe, but...
Yeah, I think I repaired a hot tub board recently. So replacing with a tantalum too.
Right.
I think it's true. The electrolytics have a lot of great uses, but I think, and although I'm not into pricing, right, I think they tend to be fairly low cost. Having said that, though, the polymer electrolytics are quite good, and the hybrid ones likewise are quite good.
They use those on PC motherboards. They have a big advertising thing, polymer capacitors, Our ones don't fail, our ones don't dry out and go bad,
Right.
So,
that's a big deal.
it's a huge sales thing on every computer motherboard advertises that they use polymer caps. You know, yeah, it's crazy. I guess they've been burned too many times in the past. Yeah, you've just got so many different types. Yeah, so.
Yeah, it's neat because we also have a hermetic tantalum or tantalum polymer, and we just achieved some flight qualifications. It's really interesting.
How do you hermetically seal that?
Well, it will use a Kyocera case and then process the thing like a standard hybrid. But we'll, instead of micro circuits, we'll have the tantalum pellets, tantalum polymer pellets. We weld them into the material system, into that ceramic package. And then we'll do the proper environment. There's a little bit of magic and special processes. But of course, we'll fill it with a non-moisture type of environment. And there's incredible performance on that part.
Wow. Yep. Do you guys where do you experiment? Because you're always experimenting with dozens of different things at once. You don't do this on the production line, do you? Do you have like a smaller R&D line? Because I assume you can't just hand make these on the bench and then, here we go. You've got to sort of put a bit more when you're designing a new cap like that, do you put it through like a mini production process?
Right. In the old days, we actually could kind of do it on the line. Old days being like 40 years ago.
Right, okay.
But I remember we came up with some types of single layer caps by getting MLCC scrap from the sides of the wafer starts, grinding it down by hand, and then metallizing it. And so it's crazy. But yeah, nowadays it's a lot different. So we've got the central R&D is for AVX at any rate is in Greenville, South Carolina. Then there's applied R&D and process R&D around the world.
So you've got three different types of R&D.
Yeah.
So can you explain the different what the different types of R&D do?
Boy, I'll get in trouble because
Oh, okay. All right. No, that's an internal thing. Okay, right. There's just different R&D groups. Okay.
Yeah, I mean,
different specialties.
They tend to specialize with some things. But the interesting thing is that we have multiple test labs around the world. And for a while, I ran a teeny EMC lab, but that got to be so big. I think there's 3 of them now around the world. And then we've got far-field chambers in France and San Diego, and it's amazing. So it's been a ride,
wow.
To see from maybe 2 factories to, I don't know, maybe there's 40 now or so.
So you've got EMC chambers, even far-field ones for testing your caps.
That's for the antenna group. So they actually have.
Okay.
Hey, there's some really neat things we can talk about antennas, and I know we're running out of time, but maybe another.
No. We can keep going. We can go as long as you want.
Well, there's active antennas that we have, and I don't do any work with those, but there's some really neat things that are occurring there to make miniature steerable types and tunable antennas. So that's potentially very impactful. But and incidentally, we also sell the chambers, test chambers.
Wow!
5G. Yeah,
really?
It's amazing how big the place is getting, right? But
AVX sell EMC test chambers.
Yes, that's right. I'll send you a link. They're really neat. Hey, and the software is so easy. It's amazing when we start looking at radiation patterns of antennas. It's so complicated, and their HMI is so wonderful. It's really allows even somebody like me to figure it out.
Right, it's excellent.
Yeah.
Oh wow, that'd be great.
The neat thing on the antennas, though, on the passives are, although there's multiple types and stamped and all of that ceramics, but when we could get those metallizations, imagine the 32 different IOs on a 1206. That allows us to have such metal control that we could have a antenna, surface mount antenna, effectively with a very efficient counterpoise. So we might have the ability, or we do have the ability, to have an easier keep out area. The keep out area is minimal with our device, so it's much easier to use with a good radiation pattern and all of that. That's the big problem with antennas, right?
Yep.
You have to have it's X amount of keep out area. It's kind of a waste.
Yeah, it's a waste. Yeah, exactly.
Right. So that's
Yeah.
a big deal. So
Wow.
Someday I'd like to show you the metallizations. It's really amazing.
Oh
what we
yeah,
can do
that'd
and
be
kind of efficiency.
incredible. What other? Oh yeah, there's the SMD. Yeah, the SSD.
Yeah.
Sorry, the SSD. Yep, that's one of the big
great parts.
applications for them. Yeah.
Yeah. So we actually rate that in terms of millijoules that we can.
Oh,
have in
okay.
there.
Oh, yes, right. Yeah, because you're talking about joules of energy, right? Where you're talking about
Right.
how much energy is required to do this X amount of processing in X amount of time. So
Yeah.
yep. Wow.
Yeah, it's a big deal. Graceful shutdown. Yep.
Yep,
And then all of our
exactly.
sample kits.
Oh, there's the multi-layer varistor you were talking about.
Yeah. Yeah, it's kind of neat
Yeah.
because it looks like a ceramic cap.
Yeah,
But
yeah.
it's a zinc oxide. And remember the old radial MLVs?
Yes.
And how those would wear out. Well, those would wear out because the grains were inconsistent. So the electric field stress would cause some to die early, right?
Oh, really?
now-
It'd just, wow. How would
That's
they
what happened
die?
in the old days.
How would they die?
Oh, they become resistive and then flame. Yeah.
Oh.
So the big old Hey, I've got a great story. So I got an Evil Knievel pinball game for $60 because they didn't realize the electrolyte or the MOV blew out
Yeah.
and it wouldn't allow any power, of course, to the machine.
Wow.
So we took that out and fixed it. So,
Oh,
but anyway, hey, these multi-layer varistors are neat because we have exceptionally tight grain size control. And believe it or not, they could take tens of thousands of strikes with no wear
wow.
out. And it's very important because it has an advantage over a TVS diode because you could take more current. With all of those multiple electrodes,
Yep.
you could divide up the current that way.
Right, yeah.
And there's also an off-state cap. So that's something you use in your favor because most of the time, this isn't doing anything, right? There's no
Yeah, exactly.
transits.
How much capacitance we talking about?
Well, it varies. You can get down to 0.2 picofarads, I believe.
Yep.
But I think we are now up to 47 or 100 nanofarads. There's so many advances. I
That's
used to be able
useful.
to remember this
Yeah.
stuff, right? Yeah, it's really
Yeah.
useful.
Right.
Yeah. So like on a relay or motor drive, stuff like that.
Yep.
And even on can
For sure.
lines, that's
Okay.
simple, right? You can replace it with one part. I
As
think
well?
there are arrays, and there's also the feed-through filter, the
yeah.
three terminal part.
Right.
So then you get a very deep notch of attenuation because these electrodes are exceptionally highly conductive. So
Wow.
that's where you could increase the effective Q of that filter, right?
And clamping.
And then there's
Ooh,
also a neat situation. So not to trash clamp diodes, because they have
Okay.
some great advantages.
Right.
What we're showing here is an X-ray. So on the top left picture, you've got a picture. It looks kind of like a teeny ceramic chip cap, right? Mm-hmm. And we're competing maybe against the DFN ceramics, or excuse me, diode. And if we do a top-down, center top picture shows the die, and it's kind of shoved in between basically copper electrodes. Mm-hmm. And those heavy copper electrodes, you can see the cross section on the right, upper right.
Yep.
And those actually act like heat pipes. So we can have a miniature die that has essentially a heat pipe taking the heat out of it. And that's where we could be on
Interesting.
the HDMI, super low cap stuff.
Right. So you got higher power handling in a smaller package.
Ultra miniature package, right? O2
Wow.
and stuff. Yep.
Very cool. That's terrific.
Yeah. Yeah, I know you did something on heat pipes in the old days.
Oh yeah, I've done a couple of videos on thermal
So
stuff
We're
and things
learning
like
a
that.
lot about heat pipes and
They're right.
where to put them in.
Yep. I wouldn't have thought about that from in that sort of package size, but it matters. I can see how that matters.
Yeah, and there's work being done actually on very high power devices with heat piping as well.
What are these RF coax things?
Well, it's neat. It's the insulation displacement connector, that is,
Yeah.
where you've got opposing phosphor-boron tines, and you don't even have to strip the wire. You just pop the wire in between the terminals, and you get a gas-tight fitting. So there's no oxidation.
Oh, gas
In
tight.
the world of,
Okay.
it's really
Wow.
neat. So in fact, I believe they're flying on some of the aircraft that were like Boeings, et cetera.
Wow. Okay.
But the RF version of that is really good for the center connector and or the center conductor and the shield. So we have a non-soldering, quick, easy to use connector for miniature coax.
Very cool.
It's brutal trying to connect miniature coax.
Oh yeah, I know. Yeah, no, it's it's horrible.
Yeah. It really is. Yeah.
So so you guys obviously do more than caps.
Oh yeah, no. And then there's some of the thin film stuff, right? We got actually 2 or 3 thin film fabs around the world, and then there's the big heavy duty stuff, the one that you could have for your table base, right? That are about the size, a couple hundred pounds. But of course, all the different types of films, and in the world of now distributed power and green power and all of that, that's becoming quite important and useful.
So how many different types of poly film capacitors are there? There's
wow, this is tough.
Yeah.
I would say we're building with 4.
4.
And there's probably 4 majors out there. PT, PEN, PPS,
Yeah. It's crazy. What are the? Can you give us a breakdown of when you would use the different types? I don't know if we have a slide here for the different applications for the different types of poly material.
Basically, here we go. Sort of. I think it was sort of on the bottom of that slide. But some of it's temperature, some of it's voltage, and some of it's just case value range.
Right.
Basically they're not like the K of multiple thousands in ceramics. Of course, they have great other properties, right?
You think that this is moisture? You're confident. How confident?
Oh, absolutely.
Absolutely.
Send me some and I'll put them on the SEM.
What would we see under a scanning microscope like that? What would we see if we did put one under there?
I might be able to see some of the, certainly we'd see some of the error or the reformed electrode on the punch through.
Okay.
And we might be able to see some of the patterning, the failure of moisture.
Right.
We'd probably try to look at the thing spectrographically as well and see what types of oxides we've grown.
Okay, so the moisture attacks the metal and then they form oxides.
Right.
Is that
right? That's
right.
That's where
is that how it
resistance
works?
Changes and yes.
So with the moisture, like it just physically eats away the metal and it just vanishes, or?
Yeah, that's basically true. It turns into oxides, and we start changing resistances. Once we start changing resistances under X amount of current or voltage, now we have a different E field. We have some heating effects that occur. Heating effects start to accelerate potentially the rate of degradation. And then if there happens to be some transient event, that could even further accelerate this thing kind of exponentially.
But if a year-old part like this fails, is it just going to be, it's just got a bad seal on it? Maybe. Is that the most likely scenario?
I think that's true, yes. In fact, I could tell you a fact. We've got, I think we've been building films since, maybe it's 25 years, and there's actually been 0 failures. Now, dead shorts, that is, right?
Oh, dead shorts. Okay, yes, because these are designed to fail open, right? These are class of capacitors. Right. So, yeah.
Right. Yeah, and some of these dead shorts would be disastrous. Imagine, windmills and large compressors and things.
So do you have any experience with the reefer caps, the paper, which they still make, don't they? I think they still manufacture.
I'm going to have to claim ignorance on that.
Okay. Oh, right. Okay. But do you know anything about the failure mode in the reefer caps? No. Okay. Because you guys have never made paper, old school paper caps like that.
Maybe in the 70s, but that's... Well, in fact, AVX was actually Aerovox. And I think there was some history. Of course, that's
right.
A long time ago.
Yep. Of course, anyone who repairs any vintage test gear from anything vintage from the 70s or 80s is if they got those reefer caps in there, you just don't power it on because they'll explode because they've got so much moisture in them.
So I carefully cut
Yeah.
the case and then put our parts on the inside.
Yeah, exactly. Well, some people do that. There's people who will actually get reefer. They'll keep the case because they want the vintage look of it. So, vintage radio enthusiasts and stuff, they'll actually keep the case. They'll actually grind it all out, all the material, and they'll put a modern cap inside the actual case and keep the case just to get that vintage look.
I do that on the old Heath kits that we rebuilt.
Oh, right.
Take out the old electrolytics. And
right. Yep.
It's neat stuff.
So moisture ingress inside a film cap can't really cause a short, can it? Is that something that you shouldn't worry about? It'll just eat away the metallization and cause a drop in capacitance.
That's right. It's just going to go away gracefully.
Right. Okay. So many different varieties, and can you use an X class instead of a Y class, and vice versa, and stuff like that?
Devastating. And now then you can throw the complexity of EVs. So inside the electric vehicle, does it have to be ACQ 200 plus safety agency rated? So it gets really complicated. I'm afraid we have to have a lawyer and data answer.
Right. Okay.
But we got the parts.
Got it. So EVs. So you're talking about for use in the control electronics for the actual battery pack itself, for the high voltage battery pack, which some of them can be 800 volts now, can't they? Some of the newer battery packs in EVs. Yeah.
There's some really impressive work going on there. And many times films are very attractive, especially as the voltage gets higher.
Yep.
And that's amazing how vehicles have changed. They really have.
Is film the only way to go for high voltage caps? No, you would use glass. You'd have glass ones, wouldn't you, for the really ultra huge ones you were talking about? Size of a cabinet.
Yeah. Well, in fact, there was a recent amount of work done by a university in America with a glass device for power drives. Now, I don't think it was practical or cost effective at the point, but they have had work ongoing with that.
Right.
Mainly what I see is electrolytics as maybe I would say lower cost possibly, but I don't know if they're low cost. But they're having some practical high voltage limitations. And I think in the future, it's probably going to be film. It's neat because, as I said before, we're starting to do some heat piping within the formed leads, but they aren't really leads. They're actually bus bars.
Right.
And you can get some high frequency response on that. You could reduce inductance. So there's a whole lot to be talked about with high power films and how to optimize the frequency response.
But with the glass ones, you'd get very low capacitances, wouldn't you? How thin? You wouldn't be able to make the glass as thin as you could on film caps and stuff like that, would you?
They actually talked, I believe, precipitating glass onto an electrode. So it was
as in like a sputtering thing,
yes.
Is that what you're talking about?
Something along that line.
Wow.
Yeah. And that's why I think it's kind of not really practical. Although, having said that, I probably made it, it's guaranteed to work now.
Right.
But it's funny. My first job within AVX was on glass dielectrics themselves, and we made thicknesses of about 1/1000th of an inch. Maybe 1.2 thousandths of an inch. And you could bend them quite, effectively maybe around a 6-inch radius or so. Maybe.
Wow, really? That's amazing.
Yeah, glass had a lot of advantages. It was exceptionally stable. It was probably the most reliable part out there. The K factor was only approximately 8, so it's not too much.
Now, on this film here, when I first started to roll it out, it was clear, and then I started to see some like a sputtering of material, and then it got more dense, and it eventually reached a point. Is that because they're sputtered, or are they actually a metal? Do they manufacture them as a film and then cut them? How does that work?
In theory, I believe the consistency of the film color should be the same from the start of your DPA to the end. However, in the start, I believe it's very easy for moisture to attack that And it's most likely because the shoopage allowed a poor, adhesion, and you got the moisture in at that point.
Right.
So I believe that's what occurred. And then, of course, as the resistance increased between the shoopage and most likely the electrode, basically that metallization just moisturized away, oxidized away,
Right.
did its job on going away. Yes. So it's actually a good point, though, because you would think that the consistency of the color of the film would be the same from the start to the end. But
Yeah. I expected just a sudden start and then boom, and then just hit a metal layer. So
and that's what you should have.
Right. So
But
is it
that's
actually a
moisture.
sputtering? Is it a sputtering process? Do you sputter the metal onto the film?
Yes, and it's continuous. So
Right.
you might go for,
Okay.
well, I'm sure it's all proprietary. So you go for
Yeah,
a long
yeah.
ways. And then
Yep.
you have these, it looks almost like saran wrap that's metallized. And then you'll cut it into the right width. And then
Yep.
you'll wind that around something that looks like a bike wheel. Well, depending upon what you're building. If you're building surface mount, you might wind it around a big diameter and then cut the...
And then chop them. Yeah, I've got a graphic for that. Yeah. Yep.
Yeah, and then if you're doing the power films, you might wind them into the size of a donut or a bagel or something like that. And then they could be pressed, mechanically pressed, to be deformed and fit more efficiently in a square box.
Oh, so squish them down to make a small.
Yeah,
That's great. That's great. Is it so? Is it all sputtering, or are there processes and types of caps that would have a metal? You would have like a roll, like you have your roll of your poly, put the kettle on film, and then you got your roll of your metal film, and you just wind them together. Is there any?
I don't know of anyone building films that way.
Were they okay? Not now, but did they used to do it that way, or has it always been sputtering?
I think there was some that occurred.
Okay.
Yeah, and
Right.
it might not have been film. It may have been another material system, but yeah, in fact, that was done. But not
Okay,
by
because a
anyone
lot
else.
of graphics out there will show that. They'll show like, oh, you've got a film of metal and you've got a film of poly and you
Yeah.
roll them together. And I guess that's too simplistic, right? They just do that for graphic purposes.
I think that's not the case anymore.
Okay,
Yeah.
right.
Yeah, but the reason would be, you probably want 100 angstrom on the electrode, and it's going to be hard to roll that out, and you're going to have maybe 1 micron to maybe 20 or so for the film itself. So it's
Right,
it's
okay.
much more efficient to do the deposition.
Right, so you'd easily lose half or 3/4 of your capacitance if you did it as a rolled metal.
Yeah, it'd
Right.
be difficult. Yes.
So sputtering. All right. Well, thank you very much, Ron. This has been awesome. I was completely wrong. I just went into this video with the mindset that it's all self-healing and I didn't think about moisture.
Well,
Who knew? Right. This is going to be a surprise to a lot of people, I think.
Well,
That
hope it's a good surprise.
It's well, it's something to think about. Is like, as electronics designers, should we avoid, if we're using them in these sorts of applications, where like a capacitive dropper, should we avoid like a no-name brand sourced cap for this reason, or are they all pretty good? Or
I don't know
all...
if I could comment on
No,
that.
you can't comment? Okay.
But I'd have to say films are a good
Yeah.
part to use, and it's probably a
Right.
great application for that.
Yep. Well, all right, it's been awesome. Thank you very much, Ron. It's been very
you.
eye-opening.
Well, next time I'll turn the lights on. Sorry about that.
All right,
It's getting dark here.
it's getting a bit dark. That's all right. No, we have been going for an hour and a half, and there will be an extended version of this. So thank you very much. It's
Thanks.
been
It's
very
been a
informative and awesome. Great. Thanks,
Thank you.
mate. See ya.
Goodbye now.